Okay, we're going to do our investigation on page 240 because we want to figure out how to graph y equals b to the x. If you're going to do it in desmos, here's a few instructions. Make sure you can see in and around the origin, kind of like where I have it. And when you type in a function, you have to use that a to the b in order to get it on there. So let's look. Let's look at a linear function. So right now I've got my linear function already graphed in desmos. We can see I have a y-intercept at y is equal to 0. I have an x-intercept at x is equal to 0, right? It's going through the point 0, 0. I have no asymptotes. I am increasing. It has a domain of x is any real number. And it has a range of y is any real number, right? There's no restrictions on this. When you go to draw the graph, you've got your dots. You've got your line, and you know that it's going through -2, -2, 1, 1, 0, 0, 1, 1, 2, 2, 3, 4, and it just keeps going. So it is a nice, simple line, right? It goes on forever and ever, so it's got arrows at either end, and that's why it's any real number, because it goes forever and ever in every direction. All right, that's not too bad. So let's come on over here and let's switch it up, and let's put in our quadratic, so just our very most basic quadratic, oops, of x squared. So we've got our swoosh. So let's write down some important things here. Our y-intercept, in this case, is also at the origin. So we've got y equals 0. Our x-intercept is at x is equal to 0. We have no asymptote. Here we're decreasing until the vertex, and then it's increasing. So it's increasing and decreasing. So it's increasing, oops, after the vertex, decreasing before the vertex, okay? And that's because it changes direction, right? Like it's our U shape. Oops. Drop you down, shrink you up, okay? In terms of domain for this one, so our domain is x is any real number. And our range for this one, sorry, I'm going to just pop it down here. Y is any real number, but y has to be bigger than or equal to 0. Right? Because our 0 is here, so y is everything bigger than 0. When you go to graph it, let's see, 0, 0, 1, 1, 2 squared is 4, 1, 1, 2, 4. And do a nice curvy, connect your dots, curvy as best you can. Okay, good. Okay, now let's see what this exponential is going to look like. So let's type this in as y equals 2 to the exponent x. Woo! Now I don't have a straight line. I don't have a curvy, like quadratic. Now I have more of just a swoosh. Okay, so let's look at that. So my y-intercept is going through 0, 1. So we can write that down. Y is equal to 1. And why is that? Well, let's think about it. 2 to the 0, well, anything to the exponent 0 is 1. My x-intercept, well, I don't actually have any, because my y equals 0 is my asymptote, because I can never sub in a value for x that would give me a 0 value. So y equals 0 is the asymptote. So what does that mean? Let's look. I typed in y equals 0, so my nice little flat line. Doesn't matter how far out I zoom, that swoosh will never cross it. And because it'll never cross it and never touch it, that's the definition of an asymptote. My function here is increasing. My domain is x is any real number. And my range would be y is any real number such that y is greater than 0. Can't equal 0 because that's my asymptote, but I am greater than 0. So let's talk a little bit more about some of these functions. Describe how the dependent variable changes as the independent variable increases. So that's saying, what does y do as we increase x? So let's talk about that one. So for my linear, y increases at a constant rate, right? That's your slope value. Quadratic, the y increases or decreases at a changing rate, and we'll see what that looks like with our second differences. Okay, that's my key. And then for my exponentials, exponential, we see that y increases at an increasing rate. And in this case, it's a common multiple of whatever that base is. So in the case here, where I had 2 to the exponent x, it's increasing by a factor of 2. Okay, because I have 2 to the x. What pattern would be looking for in a table of values for each function? So our linear functions, linear, that's when our first differences are equal. Oops. Quadratic, that's when our second differences are equal. And our exponentials, exponential, that's where you have to look for a common ratio. So what does that even mean? All right, let's set that up. Okay, so let's practice these things. So I just have a nice little table of values. So the first set of table of values is just for our y equals x function. So remember, first differences is when you take the bottom minus the top. 2 minus 1 is 1. 3 minus 2 is 1. 4 minus 3 is 1. So because my first differences are So my first differences are equal, therefore linear. Let's look at my quadratic. So here I just have the nice little function y equals x squared, because that's what we've been graphing. Again, we do our first differences. 1 minus 0 is 1. 4 minus 1 is 3. 9 minus 4 is 5. So here we have our step pattern, which is the jump between dots. 16 minus 9 is 7. So then we have to do our second differences. So those were our first differences. They are not equal. So then we're going to do our second differences. 3 minus 1 is 2. 5 minus 3 is 2. Oh, now we're getting somewhere. 7 minus 5 is 2. So therefore, quadratic, because my second differences are equal. Okay, and then last but not least, let's look at this one over here. So this table of values is based on y equals 2 to the x. So if I did my first differences and my second differences, I'm not going to get values that come out to be the same. So instead, I'm going to do what's called my common ratio. So that means I'm still going bottom top, but this time I'm going to divide. So 2 divided by 0. Okay, well, you can't do that one. Why did I do that? Okay, so this last table of values is representing y equals 2 to the x. Y equals 2 to the x. So here we're going to do what's called our common ratio. So I'm going to take the bottom, and this time I'm going to divide it by the top. So 4 divided by 2 is 2. 8 divided by 4 is 2. 16 divided by 8 is 2. So the common ratios are the same. Therefore, exponential. And that's telling me my base function. Yay! Okay, now let's see what happens when I start changing my base. So the base is the big number that the x is attached to. So right now I have 2 to the x, and I have my asymptote y equals 0 graphed. If I make my base bigger, notice how it goes steeper. If I make my base even bigger, then it's getting bigger even faster. So I can see that I'm increasing how fast it gets bigger. My y-intercept, my y-intercept is still 0, 1. My asymptote is still y equals 0. So let's write that down. So we've got my y-intercept for each case is at y equals 1. My x-intercepts, remember we don't have any because my axis, or my y equals 0 is my asymptote. The functions are still all increasing. My domain for all of them is x is any real number. And my range for all of them is y is bigger than 0 because they're always up here. They're always above the x-axis. When we go to sketch the graphs, so they're all going to go through my y-intercept. 2 to the x is going to go like that. This is a very rough graph. When I make my base a little bit bigger, it's going to go higher. And when I make my base even bigger, it's going to go, this is such a tiny graph, my apologies, even faster. So these are important things. What do these graphs have in common? Well, they have their y-intercept. They have their asymptote. They have their shape. But how did changing the base affect things? Well, changing that base, so every time I made it bigger, so the bigger the base, the faster the increase. So it's steeper. Okay. All right, we're getting there. Now let's see what happens when I turn my base into a fraction. So here I have 1/2 to the x. So it's still going through the y-intercept of 0, 1, but now we are decreasing. My asymptote is still in place. Let's see what happens when I have 1/4 to the x. Oh, now it's steeper. And if I have 1/10 to the x, oh, it's steeper still. So let's write some of this down. So my y-intercept for these guys is still equal to 1. I still have no x-intercept. My asymptote is still y equals 0, right? That's my asymptote. That's this line that they don't cross. Now that I have a fraction exponent, I am now decreasing. My domain and range are still the same. X is any real number. Y is any real number such that y is greater than 0. And now when we're graphing them, if I have 1/2 x, it looks something like that. 1/2 to the x. When I have 1/4 to the x, it came down like this. Oh boy. 1/4 to the x. And my 1/10 to the x, so when I made that base really tiny, whoa, it decreased really fast. So let's see, let's put that into words. So describe what these graphs have in common. So they still have the same stuff as the other ones. So we still have our y-intercept. We still have our asymptote. Fraction bases all have the same shape. Only now we are decreasing instead of increasing. So what happens when we change the base? So when my base is, positive but less than 1, so a fraction, a decimal, the function decreases, and the smaller the base, the faster the decrease. So that's pretty cool. Sorry. Okay, and then what would happen if instead of typing in, what I did type in, what would happen if I typed it in as negative exponents instead of the positive exponents? Well, don't forget negative exponent, that just means fraction, right? So if I type in y equals 2 to the exponent negative x, well, it's still the same. I could type in 4 to the exponent negative x, and it's still a fraction, because that's all the negative exponent means, right? It just means fraction. All right, so let's check out this last change. What happens if I stick a number in front of the base. So I'm not changing the base, I'm just changing the number in front of the base. So I've got 2 to the x here just for my comparison. So I have my y-intercept 0, 1. Okay, no problem. If I put a 3 in front of that, so if I 3 times 2 to the x, oh, interesting. Okay, how about if I stick a 4 in front? So I have 4 times 2 to the x. Ah, well, that's neat. So I've now just changed where my y-intercept is. I haven't really changed anything else, but I have kind of stretched things out here, and now I have a different y-intercept. Okay, let's write all this out, and then we've got it. So, let's not do red. My y-intercept was 1, and then it changed to 3, and then it changed to 4. So let's remember that anything to the exponent 0 is 1. So if I stick that number in front of it, if I said 3 times 2 to the 0, I'm going to get 3, because that's just 3 times 1. If I did 4 times 2 to the 0, I'm going to get 4, because that's just 4 times 1. So it doesn't matter what your base is, a times anything to the exponent 0 is going to give you a. All right, our x-intercepts, we have none. This did not affect my asymptote at all. These ones are all increasing because I used a base of 2, right? So when my base, we are increasing. When our base is greater than 1, remember we were decreasing when my base was a fraction. So when it was bigger than 0, because I needed a positive, but less than 1. My domain, as it has been all day, is x is any real number, because I can stick anything I want in there. And my range, y is any real number, y is greater than 0. So we haven't moved that asymptote at all today. We're going to move it tomorrow, but not today. So in terms of my graph, 2 to the x goes through 1, 2 to the x. 3 times 2 to the x goes through the 3 times 2 to the x. And last but not least, what do I say, 4? Well, that's not going to really fit on here very well, is it? 4 times 2 to the x. Okay, a few little righty-righty comments just to finish it all off. Describe what these graphs have in common. So they still had their y-intercept, asymptote, the shape-ish, okay, asymptote, and the effect of changing the base. We didn't change the base, we changed the number in front. So when we change that number in front, that just changed where my y-intercept was, and that's going to be our vertical stretch, and we're going to get into that more tomorrow. The number in front of the base affected the y-intercept. So there we go. That is our introduction to the exponential function.